Okay, now we should be recording. All right. So this was a really comprehensive lesson, and there were a lot of things in it, but it wasn't as dense as all the other lessons, at least, because at least I saw that it was, it's just introducing us to some basic syntax in Swift. But nevertheless, I listened to the thing twice, and I took notes, and I went through the the forum, and I ended up gathering about 50 tabs, opening up about 50 tabs on my computer of all these things that were mentioned in the forum and mentioned in the presentation to check out later. So it got to be a little overwhelming because there's a lot of papers to look at. There's a lot of Medium articles to look at, and so on. So I thought, so basically, even though this lesson has a lot of material, so what I thought I would do is to do something a hands-on. The most important thing about this lesson really is to get into the notebooks and start looking at them and playing with them. And I think if you're like me, you've been avoiding doing that. And I've avoided doing it all the way up until now, basically. So I put together this sort of a hands-on kind of an introduction where we're going to actually, and some of you, for some of you, you're going to be bored and you're going to go to sleep because you've already done this. But I thought that this would be the way to help the largest number of people who are interested here. So what we're going to do is we're going to, first of all, clone the Fast.ai docs repo if we haven't already done that, because that's where all the course notebooks come from. And then we're going to install Swift for TensorFlow in Google Colab so that we can actually run some of the notebooks. And then we're going to start looking at running some of the notebooks. We're actually going to run one or two of the notebooks. There's about 11 notebooks. There's more than 11. There's maybe 15 notebooks to run. And I've looked at one or two of them, but there's a lot. So I thought this would get everybody started so that even though we're not going to get through all the notebooks today, by using this document, this PDF document that I've uploaded to the Slack channel, this will get you started in looking at the notebooks. Now, so everyone should open up the Slack channel and get this PDF document that I'm working from. Is anybody not able to open the Slack channel? It's the fast_AI_DL channel, and I've uploaded this little presentation there. So the first thing everybody should do is to go ahead and get that. Okay, is that a problem for anybody? Or okay, all right. So let's start then. So this lesson is going to. I don't know how long it's going to run, but I'm not going to run longer than an hour. And I don't know if we have any mini presentations. There's always someone that wants to talk about something, so we are welcome to do that after we get done with this lesson. And then if there's no mini presentations, maybe we can just talk a little bit after this. Okay, so the first thing that you want to do, if you haven't already done it, is to clone the Fast.ai repo. And I've put the link here. Can everybody see this page? It says clone the Fast.ai repo. That's where I am. Is everybody seeing that?
Yeah.
Okay, thank you. So first you navigate to the Fast.ai docs repo on GitHub. It turns out that is a standalone repo all by itself. And in other words, it's not part of the Fast.ai repo. So this is what it looks like when you get there. I just did a little screen a little screen copy here. This is how it looks, the Fast.ai docs repo. And so everybody go there if you haven't, if you want to do this. I'll give you a minute to get there. Oh, and first of all, I just wanted to welcome everyone. I've seen some of you before. Some of you look new. My name's Joe Catanzarite, and sometimes I present some of these lessons. All right, so go to that, navigate to fastai.docs on GitHub, and then click this clone or download button here, this green button that says clone or download. And after you click that, you will see this link here that comes up, and then you just click in this box here to copy it to your clipboard. All right. So click this green thing that will bring down this this link here. Then you click this box here to the right of the link, and that copies it to your clipboard. Okay, so now you've got it copied to your clipboard. Now you need to open your git bash shell if you have it. Unfortunately, I didn't go through the installing Git on your computer. I'm assuming that everybody has that. It's probably a bad assumption. So if you don't have GitHub on your computer, actually you don't have to have it installed. All you have to have is a bash. All you have to have is a bash shell, I think. So does anybody not have access to a bash shell? All right, so I'm going to assume you have access to the bash shell. Open up the bash shell. Navigate to the directory above where you want to install the repo. So, so just in your bash shell, let me show you what that would look like. I'd have to share. I'll stop sharing. I'll go to my bash shell. Let's see, where is it?
Ja.
Oh, I'm not seeing it. Hold on.
Ja, jetzt sind wir. Oh, scheiße, jetzt haben wir ein Mikro.
Gotta go back.
Wie kann ich lauter stellen?
Just gonna go back. Hold on for a sec.
Joseph, just real
Yeah.
quick. I'm here in, we're here from Germany, and we are at the Meetup Spartakiade, and we just want to say hello to everybody.
Oh, hello. Is this
computer around?
Is this Philip?
This is Philip. Yes.
Hi, I recognize your voice. Right.
Hey, great.
All right. All right. So I'm going to show everyone. I'm going to share my screen where I'm going to show you what it looks like in my bash shell, if I can. Let's see. Oh, I'm share. Yeah. Okay, just briefly. So this is what it looks like. I'm in my bash shell, and I'm about to clone the Fast.ai repo that we're interested in. Okay. Now I'm going to go back and share from the presentation, and yeah. Okay. Oh, that's not what I want. Sorry, I'm got to find the PDF file I'm interested in sharing. Oh, well, I'll just share directly from the PowerPoint. It's the same file anyway. All right, so for people who just joined, please mute yourselves unless you want to speak. What we're doing is we're going through this kind of a hands-on exercise to run through and actually execute one or two of the Swift notebooks from lesson 13. Because I think that's kind of the bottleneck for most people, is actually getting in there and starting with the notebooks. People look at the lessons and they see all this material to learn. They got to read all these papers. They got to look at all these Medium posts. They got to listen to the 2.5 hour video. The real place to start is, once you've done some of that, at least listen to the video. I think the best thing to do is to dive into notebooks and start looking at them. So that's what we're going to do. And this is going to be a kind of a brief lesson where we're just going to start playing with some of the notebooks. But there's a few preliminaries we have to do to get there. The first one is to clone the Fast.ai repo, and we're now in the process of doing that. So you open up your git bash shell, you go to the directory just above where you want to clone the repo, and then you just write the command git clone, and then paste in that link that you have in your clipboard that we copied. right? So you just paste in that command and execute it. Okay. Let's see. I'm going to. Is everybody at that stage, or is there any trouble so far? Okay, so once you've done that, it takes a little while to clone that repo, and then the Swift notebooks are in the dev_Swift folder. So here's that dev_Swift folder, and then this is what let's see. This is not what I want. Forget about the page after this. It's not what I want. But anyway, once you've cloned the repo, you'll find that there's a folder called dev_Swift. That's where all the notebooks are. All right. Okay, so that's the first step. The next step we're going to do is we're going to install Swift for TensorFlow on Google Colab so that we can actually execute these notebooks. So the first thing we want to do now is go to the Swift for TensorFlow repo and I've got the link here at the top of the page on GitHub. And let's see, do I? Yeah, and there's this page that you get, and you want to go down to the usage.md file and click on that. And then there's a subsection, collaboratory, that you want to scroll down to. The subsection called Getting Newer Swift Builds.
Sorry, Joseph, could you share your screen rather than a PDF? I think we can see only the PDF.
Oh yeah, okay, so you want me to actually go through this process? I can do that. I actually did this already, so I wasn't gonna, but I'll do it. Okay, so let's go.
Oh, yeah.
Yeah, so let me stop the sharing here, go to my, let's see, go here, click that, paste and go. All right, I'm going to share that piece if I can find it. Actually being on that page. I'm having trouble finding on my screen. I have Firefox up, but here, I think this is it. Let me try this. Okay, so are you seeing now? I'm actually live on the TensorFlow repo page, I think.
Yeah, we can see it.
Okay, so now I'm going to go to the usage.md. I scroll down to the usage.md. Okay, this little markdown file. Everybody see that? It's kind of at the bottom of the menu of the list there, right? I'm going to scroll down there. I'm going to click on it. I'm going to scroll down. There's a section called Collaboratory that we want to look at, and we need to get the newest Swift build in order to do this. There's a blank Swift notebook here, but before we open that, we want to open this Swift installation notebook. All right, so I'm going to click on this. And so it brings up this little script that is executed all outside of Swift. It's all executed in the shell, in the Unix shell. And what it does is it basically takes care of all the steps of installing the Swift build. So all you have to do to get that done is click on this little play button. So I'm going to click that. It takes a few minutes actually. So let's do that.
So Joseph, one question.
Sure.
We downloaded the or we get cloned on our PC.
Yes.
I think, how did have we uploaded this to Colab?
No, that's the next step. I should explain the context of what we're doing. We downloaded, we cloned the repo on our PCs or on our individual machines that we're working on, right? And the reason for that is because that way we can access these notebooks and then we can upload them to the Colab to execute them. There may be a direct way of actually uploading them to Colab straight from the Git repo, but but I haven't figured that out yet. So the way I figured out was to clone the repo to my machine, and then once I get once I get Swift installed on the Colab, then I'm going to upload the notebooks that I want to execute onto Colab. Okay.
Have you uploaded this to your your G drive and then you're accessing from there, or you're opening directly from your PC?
Okay, when you clone the repo, it now sits in your directory structure. It's in your file structure, right? So now the next thing we're going to do after this is done, this is actually done, and the next thing we're going to do is go back to that. Let's see. We're going to go back to that page and we're going to open up. Whoops, I'm on the wrong page. Hold on for a second. Yeah. Let's see. I want to get back to that Swift page that we were at. Let's see. I'm going to have to go there again. Hold on. Swift Tensor. Yeah, I'm going to have to open up this again. Usage, open up in a new tab. Collaboratory. Okay, now in that usage, so in that usage.md, you might have to open that again in a new tab because we clicked on something and that overwrote it. So going back to this TensorFlow Swift repository, and it's just here at https www.tensorflow.org/Swift. So go there. And we're going back there so that we can get back into this usage.md document because there's a link in there that I need. So I'm going to open this up in a new tab. I've already done it. So I'm there. And what I need is this link here. To launch Swift in Colab, just open this blank Swift notebook. So I'm now going to open this in a new tab. I'm going to right-click to open it in a new tab, a blank Swift notebook. And what they said is that after we've executed that installation of Swift, which we just did, hopefully it's all finished on your machine. Now every blank Swift notebook that we open is going to have access to the latest build of Swift, right? So now we're in this blank notebook, right? What we're going to do now is go to this file menu, and we're going to upload a notebook from your own repo, the one that we just cloned. All right. So I'm going to go. I'm in this blank Swift.ipynb notebook. I'm going to go to the file menu. I'm going to go to upload a notebook. And now I'm going to browse in my own directories. You'll be browsing in your directories. And I'm going to choose the notebook that I want to upload. So here's the directory, FastAI docs. That's what you cloned. This should be in your directory structure now, right? Everybody should be able to find this. FastAI_docs, because that's what we just cloned, the first step. Anybody have trouble with this step? Finding the FastAI docs? Speak up if you do. Okay, I'm assuming everybody is now able to find their, yes.
It's still downloading. I'm still cloning it.
Oh, you're still cloning it. Okay, let's wait. Then let's wait a little bit.
No, you can keep going.
Right.
Just let me ask you a quick question. So,
sure.
The one which you did on, could you repeat the last step which you did where you went to a Swift and ran the blank? Where do I find that blank notebook?
Yes, I'll do that again. All right, so go to the page called TensorFlow. It's the TensorFlow Swift repo on GitHub. So you see I'm highlighting this link here. This is the link you want to go to. It's https.
Can you copy paste on the chat window this for me?
Oh, sure, yeah. Copy.
Yeah.
Copy link location. And if I can find chat, let's see. Can somebody remind me how I can find chat? It used to be sitting right in front of me, but now I can't see it.
Yeah, it should be on the bottom when you hover your mouse. You should see on the bottom, center bottom.
Center on the bottom. Sorry, I don't see it. Maybe if I stop sharing for a second and then I can.
That's fine.
Yeah, here it is. I find
Okay.
it. Okay. I just put the link in there.
Got it. Thank you.
Now I'm going to go back to sharing. Yeah. So here I am at the TensorFlow Swift repo. You're there. We're going to scroll down and hit this and look at this usage page. It's called usage.md. So I'm going to open that in a new tab. So I've done that. And then you scroll down. So here it is when you come in. This is the usage.md document using Swift for TensorFlow. Are you there, Dinesh?
Just 1 second. I'm getting there.
Okay. Just let me know when you got in there.
Yeah.
All right. So you're on the page that says using Swift for TensorFlow.
Yeah, I am in a usage MD. Yeah.
Okay. So at the top it says using Swift for TensorFlow, right?
Yep.
Okay.
Thank you.
Okay. Now scroll down to where it says collaboratory.
Yep.
Okay. And now it says open this blank Swift notebook. Open that in another tab just in case you need to come back to this page.
Yep. It opened. Yeah.
All right, now you've got this blank notebook. This is what it looks like when you first come in.
Correct.
Right? Now hit the File menu and then go to Upload Notebook.
File, upload. Yeah.
All right, now you get to select which notebook you want to upload. And this is where you go into your file structure where you clone the repo. On your computer. I don't know if you have it yet. You said it was still downloading, but
it's done. Okay, it's done.
Okay, great. Now your Fast.ai docs should be the top level of the repo, and then the subdirectory that we want is the folder that we want is dev Swift.
Okay, I'm going.
All right. So this is what it looks like inside of dev Swift. And now the first notebook that they used here's all the notebooks. There's actually more than 15 notebooks, I think. And I haven't gone through any of these yet. So this lesson is just to get you started so you can actually start going through them. So I'm just going to pull up the first one that they introduced in the video, which is this one, intro and float. Okay. So I'm going to click on that, and then I'm going to open it. And this is so cool. We are now inside of in Google Colab. We've opened up this notebook. And oh, I guess they copied in this installation procedure. Let's see. Okay, now the first thing we do, we get into this notebook. We're now live in this notebook in Google Colab, and we want to access the GPU or maybe even a TPU because Google Colab offers that now. So you can not only you can actually use a GPU, and to do that, you go into this runtime. You click on runtime at the top left, right? And then you scroll down to change runtime type. And this is going to allow you to access to tell it that you want to access the GPU. I'm going to click on this item, change runtime type, and then it's Swift, which is what we want. The notebook is a Swift notebook. But now go down to this hardware accelerator, and right now it's none. But if you click on this little arrow, you now have a choice of GPU or TPU. Very powerful hardware accelerators that Google is allowing us to use for free. So I'm not gonna be greedy. I don't even know what a TPU is. I think it's more powerful than a GPU. I'm not gonna be greedy. I'm just gonna take a GPU. And then I'm gonna save. So it knows that I want to run this notebook on the GPU. Is everybody up with me now? We're now inside this first notebook, intro and float. And we have to, I guess they put this installation step so maybe we didn't have to do that step before anyway. So now we're gonna run the first cell, which installs Swift. I'm just gonna click on that and let it install Swift. How's everyone doing? Is everyone up with me? Are there any problems? Anybody encountered a problem? Don't be afraid to speak up.
I got the same answer, same error as you.
Oh, really? Okay. I'm not understanding why. Let's see. So we tried to install Swift. It gave an error because why? I'm going to try something. I'm going to go back to the page where I already installed Swift here, because I think it's the same thing. Installed. No, it's not. It's not the same thing. It could be that I have to redo this. Going back to the first page, install latest _ Swift. That's the first page we navigated to. I'm going to see what happens. I think I might have to run that again because maybe we were offline for too long and I forgot that we were.
Install latest Swift.
So it's installing the late. I'm going back to the page where I installed the latest Swift. And if you lost that page, you can get to it. Let's see. On this, let's see. Yeah, it's this page that we navigated to using Swift for TensorFlow, the page that we jumped off to get the blank notebook. If you go just under that collaboratory header, it says getting new Swift builds, and I'm now doing this. Basically, I'm opening this Swift installation notebook. And I think that might be the problem is that we navigated away from it and it kind of forgot about it. So let's see. Install latest Swift. So I think on my machine it looks like it's finished. Newly installed Swift build. And so it tells you that the newly installed Swift build is version 5.0-dev. Blah blah blah. All right, so now I'm going to go back. Now all of my notebooks should have access to that. And this is I'm going back to the load data notebook, and I'm going to try again to execute this first line, this first cell. Let's see. Wait. Oh, that's not the one. That's not the one I want. It's the intro and float notebook. That's the one that we're working on, right? So I'm going to. Oh, I think there's no. I think it's okay now, but I'm gonna run it again just to make sure. Oh, try restarting the kernel. I'm not sure how to restart the kernel. Let's see. Restart runtime. So it says kernel is in a bad state. Try restarting the kernel. I'm gonna do this under runtime. I'm gonna restart the runtime. I think that's what it means, restart the kernel. Yes. And I'm not familiar with this interface to Jupyter. So in the standard Jupyter, you can always tell when something is running, and I haven't figured out how to tell that here. So, and it always, and there's also something that tells you when your kernel is restarted, and I haven't seen that here. This is a different interface to Jupyter than I've seen before. Anyway, so it's supposedly restarting the kernel. It's not doing anything though. I'm just going to reload the page. I wonder if that'll work. I'm going to reload this page. Okay, so I reloaded the page. It says initializing connected. So okay, that's how you figure it out. Okay, I'm going to try this again. And it's doing something. I'm not sure if this error text is from the last time I tried it or if that's what just happened, but I'm going to wait a little bit to see if this is going to complete. Oh. All right, I'm just going to stop that. Stop. Yes, restart that one. Okay, I'm connected now. I'm gonna. What happens if I skip this thing? Because this thing is trying to import this Fast.ai notebook, but I don't have this notebook yet. What if I just did this? Yeah, so I'm not sure what this first part is, but for now we don't need it. We can just actually directly run this notebook, it looks like. So I just ran the first cell, and they're introducing this let and bar, these let and bar commands. Let is, in Swift, you have to, you actually, it forces you to tell it what your variables are. So the let is telling it that this is a constant, this is a static constant, it cannot be changed. Batch size is being set to be a static constant that shouldn't be changed. And var is defining b as a variable. That's something you can change. So so we just did that. We printed it and it executed. So we just executed our first Swift command. Now we can run this cell. We're defining another variable and another static constant. And they're displaying some fancy stuff. In Swift, there's a way to print these Greek characters. I haven't paid too much attention to that, how he gets that. Anyway, we've done that. And this demonstrates that once you've set a static constant, Swift makes sure that you don't make a mistake. If you try to change it, Swift throws an error and says, nope, you can't do that because this is a static constant, right? So that's kind of a nice feature. It's a constraining feature. Some people might not like it, but it makes sure that it actually helps you to not commit stupid errors, right? Okay, then this one, I'm just going through. I'm just going through this notebook for the first time as you are. I've watched it in the video, but it's much better to actually execute it yourself, and then you can play with it. anyway, they were having some fun with icons because you can have these little emojis in Swift, and you know, some scatological fun here. Let's see. Now he shows you how to define a function. This is an interesting one because in Swift you have to. It's kind of like C++. You have to define the inputs, tell it what their types are. So if you're going to define a function called distance, that function has inputs x and y. You have to tell Swift that x and y what their types are. So you declare the types in the function declaration, and you also declare the output type. So that's with this arrow. This is telling you that the output type is also a float, and then directly it's just going to be x squared plus y squared. So this function is just taking inputs x and y and computing x squared plus y squared for you. So let's just execute this. Oh, sorry, it's not x squared plus y squared. It's the square root of x squared plus y squared. So, oh, and now it says we cannot use square root, right? Well, that's a problem. It doesn't have access to the function square root. So we're going to have to worry about how to resolve that, which I don't know how to do right now. Anyway, any questions so far? Yeah, so I'm not sure why it's not why it doesn't access the function, why it can't access the function square root, but that's a problem. Anyway, so yeah.
One question. So with the install, did you run any other notebook, or you just did just the install and then you got into it?
I just ran the install. So
okay.
This thing here, and it came up. You know, it successfully executed that first latest Swift, and then I actually played with this load data notebook, but we're not doing that right now. We're doing the intro and float notebook. So I'm not sure why we can't access square root inside of Swift. I don't know that. Anybody have a hint about why it's not doing that? If not, I'll just move on to the next cell where he's showing how to define a function that outputs a tuple. So he's defining this function that outputs sine of the input and cosine of the input. So the input is going to be some floating point value specified here. I'm not sure, let's see. I'm not sure what this underscore is. And then the output is going to be a tuple of floats. So the idea is that the first one will be sine of the value, the second one will be cosine of the value, and here's how that function is defined. So it probably doesn't like it because it doesn't have access to cosine, yeah. So this one crashed because we defined the function, which is probably fine, but then when we tried to execute this new function, it won't do it because it can't access these internal functions. And there's something that is missing, something that I was supposed to do, and maybe it has to do with this first thing that failed. So not sure why, but hopefully we'll resolve that at some future point. But anyway, the useful thing is we're learning how to define functions in Swift, where you have to specify the input and its type, and you specify the what's going to be output from the function as well. So this is a pretty straightforward thing for people that know Python. It's a little different, the syntax, but it's pretty straightforward. I think we can grasp it. Okay, now we can't access this, so I'm not going to try. Here is we're going to define this. So we're going to define a new static constant called tuple value, which is going to be the output of our function. So it's intended to be the tuple, which is the sine and the cosine of two 13, whatever that is. And then they're showing off this this functionality. The static constant, it's a tuple, so you can access its second value by just tuple value 0.1, and presumably its first value you could get by tuple value .0. Okay, so that's this function showing how this function thing works. Next, they show how this struct thing works. So the struct is also like a function. And in this case, they haven't defined what the output looks like. They just said that the input is going to be a variables called real and imaginary that are floating point numbers. I think this one should execute for us because it's not accessing any internal functions. And yes, it does. So we defined this this complex F, and let's see. So now we have this. We should have this variable called sum complex, and it should be a tuple which has 1 and 12 in its real and imaginary parts. Okay, I'm just going to skip down here because I don't think I think it's because we don't have access to the functionality, the square root and the sine and cosine. It's going to be hard to get into the details here because a lot of our cells aren't going to execute. The main thing I wanted to do is to give everybody a starting point where you can now start to play with these notebooks. The only thing we have to figure out.
Sorry, Joseph, just a real quick interruption. The discussion here came up why there was the change from Python to Swift. I know last week somebody alluded on that. Maybe you could comment on that real short why there was this change.
Well, I think he had planned from the very beginning that lessons number 6 and 7 of this course, of course 2, were going to be in Swift. So the idea is for these 2 lessons is he wants to start with Swift, which he's very excited about, you can tell, and for a lot of reasons that he gave in the video. And the reason, and unfortunately, we can't execute all of this this particular. I wanted to go through this notebook and show you, but the reason for going to Swift is because of the tremendous speed up that you get when you can access the compiler directly when you want to do mathematical calculations. So he showed how, maybe in this notebook, he showed how a standard calculation in PyTorch can be speeded up by a factor of 10,000 by doing it in Swift, because you can. It's basically you get C-level speed, as if you were executing directly in C. So that's the reason for going to Swift is to be able to integrate machine learning with a very fast compiled language.
Makes sense. The example with the 10,000 times speed optimization sticked.
Pardon? Sorry, Philip, I missed what you last said.
I just said it makes sense. Oh no, we have Paul. Sorry, doesn't seem to work.
Yeah, it's a problem because I haven't solved the first problem. As I mentioned, I hadn't executed any of these notebooks yet. I just spent time putting this together. This thing didn't execute the very first cell, and I'm not sure why. And I'm thinking that might be why we can't access the square root function and the sine function and so on. So we have to solve that problem, which we can probably do on the forum, and maybe it's been solved on the forums. But once you get past that, you'll be able to execute these notebooks and run through them, and that was my aim for this lesson. Now, as far as the 2 Swift lessons, as far as I can see, what Jeremy is doing is he's taking us through and reconstructing this XResNet, which he made, in the first 5 lessons, he built up to this function which he calls XResNet, where he implemented the ResNet in PyTorch, in Fast.ai, that is. And he went through a beautiful refactoring, and he got this really compact function called the XResNet model, all in one screen, just beautiful. And I believe that the goal in these next two lessons is to reconstruct that XResNet model in, at least one of the goals is to reconstruct that in Swift. And he actually gets to that by the end of this first lesson. By the end of this lesson 13, he has shown this. He has actually built XResNet in Swift, and so that's what we can look forward to going through this lesson. But I think before we get there, it's best to play with all of the notebooks that lead up to it. And so that's why I built this little lesson to get people started, because that's a major bottleneck, is to actually dive in and start playing with the notebooks. Unfortunately, there's some pain involved because we didn't get them running, but that's basically what I wanted to do. We can get this sorted out in the forums, I think, and then we'll be on our way. Any comments or questions or rants? All right. So I won't go any farther in the notebooks, but there's lots of papers to read. I think, let's see, there's a recommended lesson to go through the Swift tutorial that's on the Swift website. They recommended to go through that. That's probably reasonable to do also at the beginning. Let's see if I can find it online here, because I haven't bookmarked it. Yeah, there it is. A Swift tour. That's what it's called. It's called a Swift tour. I'm going to put. Can somebody put this on the chat while we're? Somebody can put this on the chat, and then other people, and then you can access it. Otherwise, you just Google it, a Swift tour, and you'll get there. This strikes me as something nice to go through before, maybe even before you start the notebooks. It introduces you to all the familiar things that all the basic languagey kind of things that you need to know for Swift. So it goes through how to write loops and how to, it goes through this static and var things that we just went through. Talks about how to get arrays. I haven't gone through it myself yet, but I plan to. So this is basically getting you started in understanding what Swift is. And then there's this concept called closure that I've had a little trouble with. I think what I understand a closure to be is a statement like this, where it's a complete definition of a function where you specify the inputs and what their types are, and also the output and what its type is. So here they define this function called greet, and you're supposed to be able to call greet by giving the person's name and the day. And so I think this is what they mean by a closure, a structure like this, where you specify a function, including its complete inputs and its outputs. And farther than this, I haven't gone, but it would be worthwhile. It looks like this would take maybe 15 minutes to go through, and it's probably worthwhile to do this first, and then start working in the notebooks. As far as papers to read, I haven't looked at them yet. I haven't figured out which ones are the best ones that I want to start with. And then there's also some articles on Medium, which are usually pretty useful. As you go through the forum chat, you'll see that people have referred to all kinds of links and articles and papers that are useful. And so one thing that you might do is go through the forum chat for this lesson and gather up, go through and see what people have said and what articles they're recommending to read and so on. That's also a useful thing to do. So I think I'm going to end on that note. And I wonder if there's anyone who wants to share a mini presentation or anything else.
Hi, this is Sairam, and I think I signed up to share a paper called Octave.
Oh, excellent. I'm going to turn over the share to you then, Sairam, and you can go ahead and.
Sure, just a second. Let's see. Okay. Can the folks on the call see my screen or the application?
Yes, yes, I can see.
Okay. So what I wanted to share is this interesting paper that just came out from not just Facebook. It's actually a university collaboration that Facebook had with a bunch of other universities. And what caught my attention is usually Jeremy always says, how can we make something faster and more efficient? And this was checking both those boxes. Not only was it making your traditional convolutions faster, it was also making them more accurate, which was interesting. So basically, the idea is really simple. You know that images can be factorized into two types of components. They can be low frequency components and you can have high frequency components. The low frequency components are the ones that you see in the middle picture here of the two penguins. You see that there's very little spatial variation. There's like it's sort of like a overall picture. It doesn't really show you the fine details. And you can see the sinusoidal curve that sort of goes on top of it, which is very slow varying. The high frequency component is the exact opposite. It varies quite a bit and it shows you the fine details that you see. That's the picture of the two penguins on the right. So in image theory, it's possible to factorize an input image into these two components. So they said, why not we take this idea and apply it to convolution maps, which are in some sense like images too. So their idea is let's factorize a convolution map into two sets of convolutions. You have high frequency convolutions, convolution maps, and you have low frequency convolution maps. So if you look at the figure at the bottom of this slide, you see that the traditional convolution has both the high frequency and low frequency convolution maps of the same spatial resolution. So the cuboids are basically the same size. In their proposed method, what they suggest is keep the high frequency map in the same original spatial resolution of your input, but you drop the low frequency convolution map down an octave. And that's where the paper gets its name, drop an octave and remove spatial redundancy and so forth. And the interesting thing is once they do this, they then have a method to update information between the high frequency map and low frequency map so that your convolutions go on as normal. So nothing's really changed, but everything has changed in the process. So what do you get out of doing this? Because you have a set of convolution maps that are at a lower spatial resolution, you are actually reducing the memory, you're reducing the number of flops, and therefore you're getting faster results. So that's kind of the takeaway. The second benefit that they claim that you get from low frequency maps is that when you have a lower spatial resolution, the receptive field of those filters increases, and therefore it gets a better global perspective of what's going on in the image or what's going on in the video that's been given to it as input, and therefore it can perform more accurately. So I know I just threw a bunch of ideas at you guys right now, but I'll sort of dive into each of these in the next few slides. So are there any questions at this point, or shall I just continue? Okay, great. So let's start with what an octave is. An octave is essentially, if any of you know what music theory, an octave is basically just a drop of by a power of 2. So essentially you're dividing the spatial dimension by 2. So if you've done image pyramids in the past, what you typically do is when you have an input image, you scale it down by 2 and you scale it down by 2 and you have a set of these images at varying spatial resolutions and you do a bunch of operations on them. So this is exactly the same thing, but in this paper, they're exploring only one step down. That is, from the input resolution, if my input resolution is W by H, then the Octave representation would be W over 2 times H over 2. So that's the only thing that they're exploring, but they say that we leave this open for others to figure out if going down further octaves has any benefit. Now, so I want to sort of clarify what low and high frequency spaces are. So low frequency spaces are just spatially half the size of a high frequency space. So there's nothing really fancy here. So if you have an input image that's VGA resolution 640 by 480, the low frequency version of that would be 320 by 240. That's it. It's really that simple. So here's a bunch of math where they sort of walk you through how they construct high frequency and low frequency maps. So if I have an input convolutional map X, which has dimensions C channels, a height of H, and a width of W, they're going to factorize it along the channel dimension. So they're going to factorize the convolution map into two sets of convolutions, XH and XL. XH, as you can guess, is the high frequency map. So it has the same spatial resolution. So it's still H times W as far as the spatial resolution goes, but it only has a fraction of the total channels. So it has 1 minus alpha times C. So if the original channels were 10, you're going to have 1 minus alpha times 10 channels in this particular XH map. The low frequency map is very similar to the high frequency map, but notice the difference. It has a spatial resolution of H over 2 times W over 2. So it's exactly half the spatial resolution, and it takes up the remaining number of channels. So alpha is just a parameter that controls how much of these filter maps are you going to do in the lower spatial resolution, and how much are you going to do in the higher spatial resolution. That's pretty much it. So now, if you think about what's really the benefit of this thing, you can think of it this way. So if you have more computation that you're doing at a lower spatial resolution, naturally it's going to run faster. There's going to be lesser memory consumed, and there's going to be fewer flops as well. But what they claim in the paper is that you can actually get better results with this and still be better on compute. So what is the problem with doing an Octave convolution? So your traditional convolution, you have a bunch of filters, you take your input feature map, you do the convolution, and you get an output feature map, and you go on. Because you did this factorization, you can no longer do that anymore, because half your input feature maps are in half the spatial resolution, XL, and half of them, not half of them, a fraction of them are in a higher spatial resolution. So you cannot use the same filters anymore as you would in a traditional convolution. So one of the ways that you could handle this is you could take the low frequency maps, you could upsample them, concatenate them with the high frequency maps, and then do your traditional convolution. But then this is introducing more overhead, because now you're doing the upsampling, you're doing the concatenation, and then you're doing the computation of the output map. And therefore you're losing any benefit that you would have had by doing this factorization in the first place. So what is their solution? Their solution is use separate convolutions for the low frequency maps and the high frequency maps, and then update information between them at a later stage once you're done. So how does that work? So let's just say that if X was the input tensor to a particular layer in the network, and Y is the output of that layer after it's gone through that convolution, you can factorize the output Y as YH and YL as well. So therefore your YH would receive two pieces of information. It would, so let me show you the diagram. So let me go here. So let's just have a look at this diagram. So your input is XH and XL. That's the two sets of input that's going in. Your output is YH and YL. And what you're doing here is YH gets two sets of information. The first one is XH is just done, is passed through a convolutional filter W. As usual, this is your traditional convolution with no gimmicks or anything. And then that comes as one portion of the output of YH. The second component is this information exchange step that we talked about, where XL has to somehow convey information to YH, because that's how you ensure that the convolutions are going on as usual without any changes. So how do you do that? So essentially what you do is you first convolve XL with its corresponding weight in that lower spatial resolution, and you upsample the result, and then you add it or you concatenate it to the XH output that you got, and then you get YH. Similarly, you do the reverse process for YL. So YL gets a straight convolution from XL, no upsampling, nothing. But from XH, it gets average pooled output of XH convolved with WH. So in this way, you're sort of ensuring that you're doing computations at individual spatial resolutions, but you're still sort of conveying the information that was there in the previous layer from both those sets. Is this clear, or is this a little too fast?
Hi, Ram, I have a question.
Yeah.
So what is, and forgive me, but I think you've already said it, but what is the alpha where you have?
So the alpha is the fraction of the channels that you're going to allocate towards doing low frequency convolutions. Low frequency convolution just means that you're doing the same convolution but at a lower spatial resolution. In this case,
okay.
Yeah.
Okay, so suppose you have, if it's a video, sorry, if it's a picture, it's going to have 3 channels, right?
Correct.
So what does it mean to have a fraction? You would say the fraction is what? Could it be 1/3 or?
So that's a great question. So I'm gonna answer that in an upcoming slide. So so they actually, why don't I do it and then come back to this slide? So to answer your question, so this is the slide that hopefully clarifies. So because you can't take a fraction of the input channels, the alpha in for the very first layer is set to 0, and the alpha out for that first convolution is set to your the alpha value that you have. Does that make sense? So the input image is not factorized. It's just passed through a convolution, and then every subsequent layer is going to be factorized. So that
okay.
So you are
okay. So alpha in is 0. What's alpha out going to be then?
Alpha out for the first layer is alpha. So from there on in, from after the first layer, you're going to use this factorized representation. Similarly, when you get to the output, the last layer of this convolutional network, you're going to set alpha into alpha and your alpha out to 0, because your output feature map shouldn't be factorized either.
Okay, so what if alpha is a fraction? Suppose alpha is a half, and you
Yes.
have 3 channels. How does that work? You can't have 1.5 channels.
So they round it. They round it.
It's just rounded. Okay, is it rounded down or rounded up?
They floor. So they round it.
Okay, got it. Okay.
So so to just go back here, just to make this understandable for folks. So I mean, like, instead of going into this mathematical representation here, this is a really easy way to understand what's going on. So YH, which is the output of the high frequency component of the output tensor, is a sum of the regular convolution that you do on the input high frequency map, so XH times the corresponding weight, plus the upsampled version of the low frequency input convolved with the low frequency filter. So that way your output tensor has both pieces of information. Similarly, YL, which is the low frequency map, gets the low frequency convolution as is, and the pooled output of the high frequency map with the corresponding weight. So there are 4 sets of weights that we have to concern ourselves with. So if you look at this cube, this beige cube on this slide, so you're dividing your total filters into 4 chunks. One of those chunks is going to work on the high frequency space only. So WH to H is high to high. So that's going to work only on the high frequency maps. WH to L is going to work on a conversion from high frequency to low frequency. So it's that information step where you go from the high frequency input to the low frequency output. The third component is L to L, which works on your low frequency maps only. And the fourth component is low to high, which does the information exchange from the low frequency to the high frequency. And what you should understand is, as you increase alpha, this WL to L chunk keeps increasing. And that's how you get your speed bump, because you're doing more convolutions at a lower spatial resolution. That's the basic idea. So in terms of results, what have they done? So the beauty of this approach is that you can plug this convolution into any of the existing architectures as is. So instead of doing your regular convolution, you just replace it with octconv and pretty much do the same training steps and everything else. Nothing else changes. And they have shown that they're able to beat the state of the art across a variety of models using this approach. So you can see that in this, let me slightly make this bigger. Is this better? Is this more visible now? Do you want me to zoom in to show this graph better?
No, this looks fine.
So what you should understand here in this graph is that the black dot is the baseline implementation of that particular architecture. So the black dot is with vanilla convolution, so no octconvs at all. So the equivalent of thinking would be alpha set to 0 across the board. So all these black dots are the original architectures on ImageNet with regular convolutions. The colored dots that you see after is for different values of alpha. So as you increase the value of alpha, you can see how the accuracy changes. And what you should note here is the flops here is in the logarithmic scale. So it's not a linear scale, it's actually the logarithmic scale. So you can see as you change alpha, you can see a dramatic reduction in the number of flops and memory that's required to run these, but a significant boost in accuracy. So you can see that the same model with just plugging in octconv instead of regular convolution produces a ridiculously improved accuracy score at a lower cost of memory and speed, which is shocking. And so they have done these tests not just for small models, they've actually done it across all three models. So here's some interesting results that I wanted to share. So you can see that they have, so when they say MobileNet or something like that, it doesn't have any oct convolution. When they sort of prefix the model with the term oct, it basically means that they're using octave convolution. And in this chart, they're telling you what value of alpha they're using, and they're telling you how much the parameters are changing. So the parameters don't change. That's the really interesting thing. So you still have the same number of parameters as you did before, but you have fewer flops, your inference time is faster, and your accuracy goes up tremendously. So you can see that they're able to get better results with MobileNet V1, MobileNet V2. These are small models, so you may not see much of a bump here. What's interesting is when you sort of go to the larger model. So let's look at ResNext, let's just say 101. You can see that they have fewer flops in the logarithmic scale, but they have like better accuracy as well compared to the original implementations. So this is kind of counterintuitive. Like you'd assume that if you went, like for those of you who do Kaggle competitions, you'll know that whenever you increase the image resolution and train with a fast AI CNN learner, you typically end up getting slightly better accuracy. And one of the things that Jeremy talks about is progressive resizing, where you take an image in the lower scale, train the model for a few epochs, and then upsize the image and then train it for more. This is sort of going in the reverse direction if you think about it, because they're actually operating at a lower resolution and still able to get very good accuracy. Particularly of interest is this, where you can see that this is a ResNet 152, so it's a pretty big model, but with their oct convolution, they're able to reduce the memory cost significantly, and their inference speed. Look at the images per second. It's like it's almost twice as much as any of the other ones available, and they have fewer flops, and they have better accuracy, which is stunning. So yeah, this is pretty much what I wanted to share with the group. So if there are any questions, I'll do my best to answer them.
Yeah, Saram, could you go back to that previous slide? Yeah. So what is the very last line is plus SE4 oct.
So plus SE is a variant of this. It's there was a paper that was released called Squeeze and Excite Nets. What they did is they sort of improved the state of the art on ImageNet. In fact, Jeremy tweeted about this a while back, and he mentioned that SE nets are really amazing. So SE net, Squeeze and Excite nets, I mean, you can basically plug and play into any of your existing architectures, and they outperform a whole bunch of models on ImageNet. So they were the current state of the art until AutoML came along and said, you know what, we're going to take that crown now. So what these guys have done is just taken ResNet 152 plus the squeeze and excite framework, and on top of that, just replace the convolutions with Octave convolutions. So that's what this means.
Thank you.
Any other questions? I know I rushed it a bit, but happy to. Oh, and before I forget, I did my own experiment. Let me quickly share that 1 second. Can you guys see this Colab notebook?
Yes, but it's kind of too small to read.
Let me do something about that. Is this better?
Yes, it's still hard to read, but it's better. Yeah, that's even better. Yeah, that's great.
Okay. So what I did is I just tried to take this idea, and there's this website called Papers with Code. I don't know if you guys have checked it out, but it's extremely useful for finding any implementation of current state-of-the-art papers, a whole bunch. So what they do is folks, third-party implementations and official implementations are all logged onto that website. So for any given paper, you can actually find implementations in a variety of frameworks like TensorFlow, PyTorch, you name it. So I went to that website, and as expected, there was a whole bunch of implementations for octcons. So I just borrowed one of those implementations and tried it out on a Jupyter notebook just to see if this really works. So I tried to evaluate this on Cypher 10, which is a 10 class image classification challenge dataset. This is the traditional thing that that all of us do in Fast.ai. And just to make sure that the data is sort of fixed for both, I sort of just created the data bunch once and just use the same data bunch. So that way you fix everything, the order in which the training examples are seen, the validation set, all of those things. So here I'm just preparing the data. There's nothing really fancy. We're just doing some transformations, and we're normalizing it by the ImageNet stats. So that's our data bunch. And you can see that these are some of the images. They're extremely pixelated because these are 32 by 32 by 3 images. So they're really small. So you're not gonna, but you can make out what these are. I mean, it's sort of understandable what these are. So this is the OctConv implementation. I'll share this notebook with all of you after the session. So this is the GitHub repo from which I got the implementation. However, I noticed interestingly that the OctConv was about 4 to 5 times slower than the ResNet 50 that PyTorch has, which I have no idea why. But the author of this particular implementation has also acknowledged the same thing. He said that I don't know why this is slower, and I'm going to try to debug it. In the meantime, Facebook has released an MXNet implementation of this paper. So for those of you who are familiar with MXNet and know how to port it to PyTorch, there's a challenge for you, so you can try that out. Anyway, so I'm not going to run through the code too much, but essentially he's replaced all the regular convolutions with this octconv. So this is the only part that I want to discuss with all of you. So you're basically having the same kind of structure that you would for a regular convolution. You have input channels, output channels. The only additional term here is the alpha term, which tells you how many, what's the fraction of channels I'm going to convolve at a lower spatial resolution. And that's all you're doing. So you're basically saying, given my input channels, I'm going to multiply it by alpha to decide how much of these channels are going to be in the low scale and how much of these are going to be in the high scale. Nothing else. But after that, it's exactly the same thing. It's like nn.conv2d. There's literally no difference. You're doing the chiming in it, you're doing regular convolutions. And then at the last step, what you're doing is, like I showed you in that figure, you're upsampling the low frequency maps to the original, and you're average pulling the high frequency maps down to the low. And when you look at the forward pass, that's exactly what goes on here. You're basically producing these convolved outputs, and then you're saying that this is the output. So the low output is the low frequency map convolved with the low frequency weight plus the high frequency map to low frequency convolution operation, which is basically just going to, it's going to take the high frequency output and move it to a spatial resolution of the low frequency map. The same thing happens for the high map, as you can see here. So that's literally it. And then after that, they're just defining all the other modules as you would for a regular ResNet 50 or a ResNet anything. So you have your 3x3s, your 1x1, you have your basic block, you have your bottleneck. All of those implementations are exactly the same. The only thing that changes is the function call. And if you look at the function call here, instead of your regular convolution, you do Octave convolution. That's literally it, which is fascinating because in theory, you can take this and then run with it on any of your models that you're training just to see how it's working. So I ran this for a ResNet 50 with our Fast.ai library. I set alpha to 0.25 and I tried it out. As you can see, it takes 3 minutes and 46 seconds per epoch, which is shocking, which should take much less than that. So I'm going to debug this implementation and try to see what's wrong, why it's not running fast. But just for reference, this is from the PyTorch official repo. So I've just taken their code for ResNet. I haven't made any changes to it. And using the same data bunch and all other parameters remaining the same, it takes 52 seconds for the vanilla ResNet, which is shocking because this means that the octconv implementation is about 3 to 4 times slower, which is puzzling. So I also did sort of a study of the other implementations in that papers with code website, and I found that a lot of these third-party implementations report the same thing. There's actually a couple of implementations in Keras that say that they've actually benchmarked it and they say that they get better results. So I haven't tried those out, but all the PyTorch ones are suffering from the same problem. They're all slower than the vanilla convolution. So yeah, so I'll share this notebook with you guys on the Slack channel. But that's what I wanted to share with all of you.
Thanks, Saurabh. That's really fascinating. Hopefully, we can sort out why the authors are getting world-class results and you're not.
I mean, for one, I'm not working at Facebook, so
yeah.
But
yeah. So presumably they claim they get world-class results and it can be demonstrated and repeated by other people. So I guess. Yeah.
There seems to be a couple of repos. There's one in MXNet now from Facebook itself where they benchmark their results, and there's one in Keras that the Facebook folks pointed to saying that this is a good third-party implementation. Both of those have benchmark results, and they've shown that for their experiments they're able to see this improvement. I have a feeling there's a trick that's being missed in the PyTorch repo because depending on whether you're using the functional API or something else, your performance or mileage might vary. But I'm going to dig into this a little more because I think it's a really useful thing to implement and use in various projects.
Definitely. So we'll look forward to that. It seems like it's related to in some way to wavelets. I mean, looking at different spatial resolutions and combining them to get a better handle on the predictions.
Right. That's a great analogy. It certainly does feel like wavelets.
And so you would think that there's a possible scope to expand it at the expense of time and compute time and flops, to expand it to more octaves. In other words, go a factor of 2, a factor of 4, a factor of 8 if you can, and that would take a bit of writing to get a routine to do that, and it would probably be a lot more compute overhead, but maybe that would even give a better result.
I suppose that they take the hit on doing multiple levels of convolution Because if you do a larger portion of those convolutions at a lower spatial resolution, the gains there outweigh the overhead that you encounter when you do
I see.
all of these jobs. That's the basic.
I see. So maybe just one. Maybe it would be interesting to try just one more level. Go to a factor of 4, and then see if that gets even better than the factor of 2.
Right.
Anyway, that would be a lot of work, but that would be an interesting thing to try.
Right. Definitely.
All right. Well, this is really great. I saw that paper and I wanted to understand it, but I didn't have time to read it. And I think your presentation was great. It gets me the basic idea, and I can go back and read it, try to understand it. So I was wondering if Christian and your group over there, Michael, I see you, and I think Philip's there. Have you got anything you're at some fancy conference in Germany, and have you got anything to report from there? Anything interesting that you've heard or you want to talk about? Can you unmute? Can't hear you. Audio is not coming through. Can anybody hear Michael?
No.
Okay. Michael, you show us unmuted, but somehow the voice isn't coming through.
Can you hear me now?
Yes. Yes.
Sorry. Yeah. I think Christian's organizing some sort of data science workshop or something in German Alps. That's going to happen soon, I guess.
Mm-hmm.
So I think that's what he's going to do. But for now, I'm not attending any special event.
I see.
I would like to.
Yeah. Is anybody else then? Anybody else have anything they want to say?
Yeah, I've got a question. Maybe if anyone experiencing. So what I want to do, I want to cluster images. So I'm not sure, is there like a PCA for images, or anyone experienced in such a way? Or also heard maybe you can use GANs for or autoencoders. I just never done that, and thought maybe is there anyone in the group who's familiar with such a thing? So like semi-supervised things. So there are some labels, but not so many, and I wanted to get more like granular representation of those kind of labels. So I want to just throw them at some sort of like PCA for images. I don't know what that is yet, but yeah, that's what I want to do. So I just wonder whether maybe someone did that before and can share some resources.
So you want to, you have a bunch of images and you want to classify them in similar categories or something like that?
Yeah, exactly, yeah.
So
something like the Platform AI tool, but more like in a code way, so you can code it and get the repeatable results.
I was thinking you could, I was thinking you could, this is just a simple, okay, can somebody mute in the background? I'm hearing some kids. Some kids are present. Okay, good, that's good. So yeah, so I was thinking, just off the top of my head, is that you could downsample the images, somehow sample them down to a very small, like 32 by 32, and then convert them into vectors, and then try to do clustering on those vectors in space. You know, you could take the 32 by 32 image and then maybe embed it in some lower dimensional vector, and then try to do clustering on those lower dimensional vectors. Does that make sense?
Yeah, I can try that for sure. Thank you.
I mean, the simplest thing would be a three-dimensional vector, so you could actually visualize it, you know. But I don't know if that would work, or if that would give you any degree of separability in the classes.
Yeah, I'll try that for sure. I think there are also some kind of like a tools that you can cluster images as well, but I need to kind of investigate what they are.
Yeah.
When I was listening to Lex Friedman podcast with Ian Goodfellow, he mentioned that GANs also used for that purpose in some way. So maybe I need to also do some research on that.
Yeah, I'm behind. I saw that that video come by, and I just didn't have time to listen to it. I think it's really hard to keep up with all these because Sam is so good at putting out, you know, it must be like 2 videos every week, and I can't keep up with them. But I want to listen to that.
Yeah, that's right. Thank you.
Okay. Anybody else? We've got 5 minutes to go. I guess there has been some conversation on the with Sam, going back and forth with a bunch of us and Sam, trying to figure out what to do with this group once these lessons are over. And I think that we have one more lesson next week, the final lesson, number seven for this course, and it's the second of 2 in Swift. And then the course will be over, except that Jeremy says he wants to tack on a couple of lessons on the end. And I think he was going to do something about audio files, so we'll see. But anyway, after those are done, then we're done with our course, and we need to figure out where to go next with this study group and meetup. And so a couple of ideas that have gone by is, since there are basically 3 groups of learners. One is us, the people who have gone through course 1 version 3 and version 2, and who are also going through course 2 version 3 of both courses, and we're almost done with them. That's one group, and we want to continue learning. There's another group which is people who are now going through the course 1 version 3 at various stages, these learners. And then another group is going to start in June when the course 2 version 3 becomes live online. It becomes a MOOC. Then there will be people who are starting that for the first time. And it would be good if our group can, if this meetup can serve all 3 groups by continuing in some way. And Sam suggested something interesting. He said that maybe we could have 3 different meetups that all occur at the same time on Saturday. We split off 2 new groups. That would be the course 1, people who are studying course 1 version 3, and the people who are studying course 2 version 3. And each of those groups has their own meetup. Each of those groups becomes a separate group, and we canvass the field. We canvass everyone for who wants to moderate that. So, you know, we can get people to actually conduct the lesson reviews and so on. And then Sam's suggestion was we have 3 parallel sessions on Saturday, 1 for each of these groups, and then our session continues as is, and the 2 new sessions continue in parallel for an hour. And then at the end of the hour, we all 3 groups join for a common session where we listen to mini presentations or have just chat. And I think for this purpose, the second part of the meetup probably should be extended to an hour because now there'll be more people in it. And that way, you know, people could join just for the first hour if they want, and then if they don't have time, they don't have to even stick around for the second hour. Or people could, if they don't have time for the first hour, they could just join during the second hour to get the mini presentations. What do people think about that?
I think since the topics are so important, people should hang around for the 2 hours.
Of course, but they may not be able to. I mean,
yeah, that's true. That's true.
This would just add that flexibility. They could just do whatever they wanted.
True. Yes.
Yeah. Yeah. So we'll keep that going and see where that goes. But I think that would be a good way for our group to evolve in the future.
Yeah. So I like the way that the split for like more advanced, maybe that's the way to call it, people who went through part 1 and part 2, and then the guys that just starting. So that's maybe a good thing.
Yeah, and the community itself, we can ask people. There's always going to be, in every group, there's going to be people who want to lead and who want to do something and organize, so they can organize the meetups the way they want for their group, for the course 1 group and for the course 2 group. We've already got ourselves organized for the course, for the what quote unquote advanced learners. And for our meetup, it would be good, I think, I don't know what your feelings are about this, but in the interim between now and June, once he finishes these lessons, for me, I would like to go through and have a second pass at course 2, because these lessons have gone by so fast. But I feel like I've gotten something out of each one. And I would really like to go and have a second pass in which we explore things a little more deeply, read some of the papers, really spend some more time with the notebooks, and get more out of them. So that's where what I would like to do between now and June, if people agree.
Yeah, that makes sense. It was a lot of stuff to take in. I guess even 7 weeks, it's not enough. Another 7 weeks is not enough.
Yeah, right. Someone was planning to go through everything, and he said, I forget, one of us, he made a comment saying that his plan was to spend 16 weeks going through course 2.
Yeah, it's basically one notebook per week, because sometimes Jeremy showed like a couple of notebooks per one lesson, and then just like, let's do one notebook per week, and that's plenty already.
I think that's right, and if we had time, that would be great. So that'd be great to do that.
Yeah, I agree that we have the opportunity to maybe get some more people on board, as the part 2 will be available sometime in June. We don't know that date. That's the kind of tricky part.
That's right.
But at the same time, we can just say we don't need to start the study group the same day the course is live. We can just say in advance, like say end of June maybe, or whatever dates works for us.
Yeah.
And
and other things we could do, other possibilities are going through forming ourselves on Kaggle to do Kaggle competitions too, because I think that's another good way to learn, is to there are actually 3 things. There's 3 ways to learn. One is to actually go through the notebooks in detail and understand them. The second way is to do Kaggle competitions, and the third way is to come up with your own project. And all of these things can be worked in parallel if you have enough time. So, but the problem is that many of us are working, and there's limited time. So.
Yeah. Well, I was also thinking about, what Jeremy teaches us is more like a research, the deep learning research. I was also thinking to add to that some more practical aspects, like dealing with data sets, getting them from somewhere, maybe putting the models into production-like environment. That's of course a completely different topic than the course. It's something that Jeremy doesn't cover.
No, I think that's great, because I'm looking for a job right now. I don't know about any of you, but a lot of the jobs in machine learning, they want you to know everything about machine learning, but they also want you to know everything about being a data engineer, which is exactly what you said, putting the models into production, building the infrastructure. Yeah. And I don't really want to become an expert in data engineering, but I do want to understand basics of it, and so that I could do it, so that I'll understand when I get a job as a data scientist and I talk to the data engineers, I'll understand what they're doing and I can help them or whatever. I want to understand enough about data engineering to be dangerous, but I don't really want to specialize in it.
Yeah, that makes sense. I don't know whether there's any course available about that topic, or without going too much into detail, as you said. I don't want to also become like an expert in that, but just to understand enough, I guess. But I'm not aware of any course like that. Maybe there is one.
Yeah, but there is a section on the forum, which I haven't paid too much attention to, that is exclusively devoted to productionizing models in the Fast.ai forum. I bet that would be a great place to start. But I haven't paid much attention to that. Yeah. All right, well, we're at the end. We went over by 4 minutes. I want to just bring things to a close and thank everyone for coming, and especially Cyrem for the wonderful presentation you did on the OctCon. That's worth looking into. And I guess I'll see you all next week. And thanks for joining us, all of you folks in Germany. I see the weather is really nice. It must be the evening over there. We'll see you next week then.
Yep, thank you.
Okay.
See you next week.
See you next week.
Okay. Bye everyone.
Bye.